Hello everyone, my name is Xiulong Liu, coming from Tianjin University, China. Today I'm gonna present a paper entitled RFID and Camera Fusion for Recognition of Human-Object Interaction. Here I will give my presentation following the 5 parts. At the very beginning, I will show you the motivation and problem statement. The promising technologies such as IoT, big data, and AI have brought us into the age of cyber-physical systems, and the deep fusion of human and physical world is making it evolve into the next stage called human cyber-physical system. To achieve this objective, one of the key technologies is human-object interaction technology, which recognizes human gestural interactions with physical objects. There are many practical applications. For example, in a library, as a reader walking through bookshelves, he or she may interact with a tagged book by waving the hand to query the book's theme or recommend similar books for comparison. In factory, a production operator may draw a cross in the air with a specific tagged part to alert quality issues, thereby automatically generating a quality report. In a smart home, a user may take out a food item out of fridge and perform a specific gesture in the air to find out the expiration date or possible cooking recipe. This technology may help build the metaverse in future, because it can open a data channel from the real world to the digital world. In this work, the problem can be defined as follows. Multiple subjects and multiple objects coexist in a application region where sensing devices such as RFID, WSN, or camera may be deployed. Each subject may take an object in hand to perform a gesture, for example, a drawing letter or a symbol in the air to express a specific meaning about the object. And our objective is to find out who takes which tagged object and draws what in the air. There are already some solutions which are divided into two categories. Some works focus on gesture recognition. They use different sensing technologies such as Wi-Fi, CV to recognize gesture user performed, but they can't exactly identify the individual objects held in a person's hand. For example, items of the same brand are usually too similar to be distinguished by the computer vision technology. The other works focus on object tracking. For example, they track the finger's location or the item's location, but they fail to recognize the identity of a subject who interacts with the item. Worst of all, they fail to work in multi-subject and tag-dense application scenarios, which is a very common demand. To overcome the limitations of existing solutions, this paper proposes a multimodal recognition system named RF camera. RF camera mainly includes 3 parts: an RFID reader with an antenna, an isoconnected DK having a depth camera and an RGB camera, a backend server. After each successful tag reading, the reader can report not only the tag IDs but also some low-level data about the tag signals, for example, phase, RSSI, Doppler value, and timestamps. In this work, we use RFID phase signal to achieve tracking. This is because the phase information is linearly related to the distance from the tag to the antenna. The depth camera can simultaneously track multiple human bodies and report the 3D locations of 32 joints, for example head, neck, and hands, of each subject skeleton in its coordinate system. In this part, we will first present the overview of the proposed RF camera system. As you can see, the system consists of four major function blocks: data collection, gesture recognition, human identity recognition, and human object matching. First, in the block of data collection, when one or more subjects are within the monitoring region of RF camera, the cameras of Kinect will continuously report the skeleton data of each subject and the normal RGB figure to the server. As a matter of fact, we only care about the intentional gesture actions instead of irrelevant actions such as randomly grabbing objects or moving hands. So we should find a way to extract effective data. To extract the effective data corresponding to the intentional gesture actions from the whole noisy sensing data, we propose a state transition diagram. We leverage the key time points to extract the factory camera data and RFID data as well. However, with the Aloha communication mechanism, tags compete for a limited time slot in a narrow RFID channel. In RFID tag dance scenarios, each tag can only has a few chances to be read. The sparse face data will cause incorrect unwrapping, which significantly affects the accuracy of gesture recognition methods. Hence, to keep high accuracy, it is necessary to investigate how to improve the reading rates of target tags. To address this issue, this paper proposes a CV-assisted RFID scheduling method, in which the server controls the RFID reading operations on visual analytics of human gestures. We dynamically update the RFID mask according to the human drawing state using instance sampling of RFID and Kinect data. As a result, we can see from the bottom figure, the face data of these two tags can be well unwrapped due to the sufficient tag readings. Second, in the block of gesture recognition, after extracting the hand-moving trajectory of a subject and apply the UKF to smooth it, to reduce computation complexity, we use the ransack algorithm to find the best fitting plane and project the hand-moving trajectory onto this plane to achieve a 2D figure, which can still well maintain visual information about what the subject draws in the air. We use data augmentation to acquire gesture database for letters or graphics. We use such datasets to train our self-designed lightweight deep learning model. In reality, after a subject draws a letter or graphic in the air, we also use the bow dimension reduction method to obtain real-time 2D figure and feed it into the trained model to achieve gesture recognition. Third, in the block of human identity recognition, to improve the efficiency in multi-subject scenarios, we get the locations of subjects' three key joint points, which include left shoulder, right shoulder, and nose, using the alignment functions provided by Kinect KD library. We can extract the facial image from RGB figure by coordinate mapping and feed it to the server to find the human identity. In the last block, when a subject draws in the air with a tagged object in hand, the face data received from the held tag will change because the distance between it and the reader antenna changes over time. So a challenging issue is how to leverage the change of tag face data to distinguish which tag is actually held in the target subject's hand. Our solution is to fuse RFID and computer vision technology. When a person draws a gesture with an RFID tagged object, Kinect is used to obtain the hand trajectory and RFID is used to obtain the item information. We first use the hand trajectory in 3D space to predict how the face data of health tag will change. That is the virtual face data. Then we compare the predicted virtual face data with the real face data of each tag using DTW algorithm, thereby recognizing which tag is held in the target subject hand. However, due to the different sizes of objects, we cannot simply treat the trajectory of hand as that of the held tag due to position of sight between hand and the tag. Through initial observation, we make an empirical assumption that the vector from hand location to tag location keeps relatively stable during the drawing process. Therefore, by establishing the coordinate system for the RFID tag and the human hand, we enumerate the offset vector and eliminate using the maximum likelihood estimation. Finally, we use DTW algorithm to obtain the best matching object of the highest probability. In this section, we will show the system performance. The hardware of system combines a Kinect RFID system and an edge server to perform intelligent processing. As for the impact of the subject number, we achieve high accuracy, about 9% in 1 or 2% cases. Recognition matching accuracy generally decreases with respect to the number of involved subjects, which may be caused by human multipass and so on. As for the impact of subject-system distance, the accuracy is generally about 90%, with the subject-system distance varying from 1 meter to 2.5 meters. RFID and camera raw data are relatively unreliable for subject system distance in 2.5 meters. As for the impact of hand tag offset, the gesture recognition, human identity, human object matching accuracy generally decreases with the increase of hand tag offset, ranging from 10 centimeters to 40 centimeters. As for the impact of human habit diversity, different subjects have different drawing behaviors, affecting some gesture recognition. For example, as for the same gesture G, S2 achieves 95% accuracy, while S6 is below 80%. In the last section, the contribution of this work are summarized as follows. Thanks for listening.